So welcome everyone to the final lecture of our online training course. I hope that many of you have seen most of the lectures, and this is our 17th one, so the week 17. And I have the pleasure to introduce to you Dr. Bror Johnson. He is a senior scientist at Plymouth Marine Laboratory in the UK. He holds a PhD in physical oceanography from Stockholm University in Sweden and has previously worked at Princeton University and the University of New Hampshire in the United States. Bror's research interests lie in the interactions between physical processes and marine ecosystems, and he's interested in the temporal and spatial scales on which different processes control biological production and other processes. He's also interested in the connectivity between different regions in the ocean and its influence on biogeochemical cycles, as well as how to combine in-situ observations, remote sensing, and modeling to better understand marine ecosystems. And today he will be speaking on how to use Python for Earth observation. Bror, the floor is yours.
Thank you. So I was going to try to share my screen, see if this works. Is this correct?
Perfect, yes.
Awesome. Thank you everyone for coming. And as you might have heard, this is the final section and the final module of this lecture series. So I should have gone out with some kind of huge crescendo, but it might be a little bit more fizzle because I'm going to try to go and be very down to earth. And it's going to be a lot of broccoli eating at this talk because you've seen a lot of other presentations showing the potential of data processing and analysis using different methods and different platforms and different languages. The language that's being used by far the most often is Python. And Python is also a little bit of a broccoli or meat or potato language. So I'm going to try to go through a little bit about how to think and how to take this to a next level. What can you do? And what should you think about when you go and continue this work when it comes to Earth observation data and data processing? Just want to start with really put us down and do some kind of basic, making sure that we're on the same level. Because of course, I don't know where any of you have, what background any of you have and what kind of knowledge you have. So I'm kind of going to assume that you're all interested and that you want to work. Please try again. Sorry, that was my Siri started talking. And that you want to work with this, but you're not an expert, but you have an interest. And I should say that when it comes to having a computer, the ability to do data processing and data analysis is something that's useful for absolutely everyone, no matter where you are in your career and what your interests are, because that allows you to at least look at and work with certain data sets. You're not depending on other people to help you. And I'm going to try to set this all a little bit into a context. So when we talk about data processing, people have very different ideas what you mean. And you can think of it as three kind of distinct categories of approaches. One is the one that everyone has done, which is the Excel spreadsheet, or pulling data from a web portal, or looking into some kind of very pre-digested output from a software. Ocean Data Viewer is an example for the people of you that are more of oceanographers. The green part here is very useful when you just want to look quickly at something small and you want to have an idea of what's going on. But very quickly you come to a point where you want to process data and you want to do it automatically. Doing so, you normally use what's called a scripting language. And a scripting language is a little bit of a way of combining different components. This is something that's been used for a very long time in the Unix world. The third large type of languages that we're talking about, so these are computer languages, are the compiled languages. These are the ones that when you want things to go really, really fast and you're processing tons and tons and tons of data. And the kind of language that we're talking about here are on the Excel side, of course, Excel. And then in the middle, the most commonly used languages for our purposes are R, Python, and MATLAB. Gail gave a really nice presentation on Julia, which lies somewhere between the scripting and the compiled languages. And then the compiled languages are Rust, C++, and Fortran most of the time. VBA is the way of using Excel, and Excel as a scripting language. And the reason I'm mentioning this is that if you go and talk to someone in your lab or in your community or a relative and you ask them, oh, I want to do data analysis, what should I use? They will mention all of these words and they will use it as many times the truth. But I just want to show you here how to interpret what everything means. So the languages in the middle are, as I said, R, Python, and MATLAB. And the reason why we all look at these languages more than anything else is what's called the science stack or the numerical stack. What this is that a language that we are using for data analysis needs to have certain kind of capacities. They often are able to do some kind of linear algebra and matrix manipulation. And the reason for that is that we want to be able to work with data as if they are in a matrix. So we have an x-axis and an y-axis, and we can say that something to the right of something else is also to the right of something else in space. Or so you have this gridded idea of how to look at data. You want them to be able to do a lot of numerical computing and have very good performance. And then there are tons of smaller things that are really, really important. Things like being able to have a big library of algorithms, to be able to do statistics, to be able to plot your data, to be able to do read and write to different kinds of data. Preferably be able to do cartography and be able to work with machine learning and have an ability to do parallelized computing. And all the languages I just mentioned can do this. But the benefit with Python, which, as I said, is the broccoli language, is that we can do all of these things with Python, but we can do many more things. We can use it for web applications, to develop desktop graphical user interface. We can use it for finance forecasting, for a bunch of enterprise applications. So this kind of this boring language that everyone is using for all these different kind of things. That doesn't mean that other languages are not very useful as well. So as I said, the Rust, C, and Fortran family are really, really fast. They are hard to work with, but they're really, really good at doing things fast. R is an amazing language for statistics. So if you want to develop statistical methods, there probably is a foundation in R to do that. This is what statisticians and public health people really, really like. MATLAB is great because you have tons and tons of modules that you can use for doing geospatial development or GIS or machine learning. And MATLAB is expensive, but it has tons and tons of ability there, and you can always get help to do development. Ideally, something we shouldn't talk about because we don't use that anymore, and we prefer not to mention it. It's just a quick joke. It used to be used in system sciences a lot, or in Earth observation a lot, but it has kind of gotten out of fashion for different reasons. JavaScript and TypeScript is being used for tons and tons of stuff, but it's not that commonly used within science. Neither are Go, Java, or C# or F#. They're good languages, but we tend to not end up using them for our purposes. And then, as I said, Python is this kind of jack of all trades. Julia is great in this kind of context between scripting and running large data code because it's very, very fast. But Julia is also very specifically focused on science cases, whereas Python is a very general language. So if you learn Python, and what I'm trying to do here is motivate you to learn Python. If you learn Python, you can use it not only for your science cases, but you can use it for web services or for many, many, many different cases. And what you want to look for when you start to invest time in learning a language, and when you start to build up a code base for whatever you want to do, are certain characteristics. You want it to have consistency. You want everything to work kind of the same way, so you don't have to relearn the everything all the time, because that gets really annoying. You want to have a large ecosystem so that you know that you can be able to do tons of different things with one knowledge base. You want to have community support, basically that you can ask questions. There are people that can help you. There are people that can help develop things for you. Many vendors, coming back to IDL a little bit, is that you want to have companies that are investing in the ecosystem so that you know that people, that things are moving forward, and that there is kind of a little bit of push to get new methods, new ideas, new technologies implemented rather quickly. Upstream adaptation, well, actually should be downstream adaptation, means that you want the guys that you're working with, NASA, the people behind NetCDF, the machine learning people, you want them to also use the same language as you're doing. And you also want to have a focus on the long term, because you might be writing code today that you're going to come back to 5 or 10 years ago. So even if you have the gadfly that is extremely popular right now, if that's not around 3 or 5 years from now, you might be in trouble. And that's something to really think. So, okay, Python is great, but everyone knows that Python is also extremely slow. So why are we working with it? What is the deal with that? Well, what Python is good at more than anything else is to function with what's called application programming interfaces, or APIs. And what that is, APIs is a way for computers or computer softwares or computer processes to talk to each other. So even if Python in itself is slow, it's able to communicate with other entities and do things that can do this very fast. And as an example to show this is where we are very often when we're working with Python, is that we have Python as one entity, and we have a data object. We have this huge NetCDF file that we want to work with, or this in situ data set we want to do something with. And Python can communicate with that data object. So a data object is just a pile of data in one form or another. And then you have, when you work in Python, what normally you do is that the actual calculations, the actual work that is being done, is done in a separate process that is written in Fortran or C or Rust or any other really, really fast language. And that entity is interacting with the data object a lot. And you have all the speed there. And what Python is doing is just kind of like, all right, let's start up this and see what's going on, and then wait a little bit, and then come back and do this. So Python is kind of just facilitating this work between the Fortran process and the data object. It looks complicated, and it's something that was like, well, what do we all talk about? But this is not something you ever have to think about if you do things right. I'm going to come back later to why you need to know this. Well, actually, I'm going to come back to it right now. This is an example, and this is the first piece of Python code I'm going to show you. For most of you, this might be completely gibberish, but for you guys, for the people that are starting to play with Python or know Python, I'm just going to go through this very quickly, because there are some basic foundations around Python here that we can talk about. So for the first line here, where it says import numpy as np, what this is that in Python, which is different from other languages, is that you need to tell Python which part of the language you want to use at different times. And numpy is this kind of workhorse that we always come back to. That is the scientific stack for Python. So you need to add that. What the second line does is just create an array that's 100 by 100, and we're going to of ones, so the number 1, and we're going to multiply that with 2. So now we have an array with 2, so make a matrix with 100 by 100 twos. And then we're going to create a third variable that is the ones with 100 by 100 but times 3. So now we have a matrix with 3s, 100 by 100 matrix with 3s. This third one is just zeros. And then, so this is how you work with NumPy, how you create something in NumPy, how you create variables. And then then the next step here is the loop. So we're going to create a loop here. So we're going to loop through the value from 0 to 99 in this case. And we're going to do that with the IPOS as the variable. And you can see that loops are written very, very specifically in a very specific way in Python, because indentation is very important. So you see the for loop, the first line with the for is where we start the loop, and then we have an indentation which says everything else here we will run within the loop. So basically what this loop does is take this third array, and for each element, for each position in this array, we're going to add the element in array A and the element in array B. Awesome. This is a terrible way to do it in Python. Because what you should do instead is, as I said, using these ideas of interfaces and APIs instead. So on the second piece of code that I just showed now, we have the first two lines are the same, but the third line, all we're doing is that we're doing array A plus array B. So these two pieces of code does the exact same thing, but what we're doing here is that when we do array A, is that we're creating a data object that C++ understands, and then when we create array B, we create another data object that also C++ understands. And with the third line, we take those data objects and in C does that combination. So that means that Python doesn't have to do all that work, and therefore this is much, much faster. So when you work with Python, when you start playing with this, try to never use loops, because loops will be very, very slow. This is the same thing in R and in MATLAB. They have this same structure where we are working with big data objects that we're moving around, and then we kind of crush them together, or we do manipulation between them or on them, but we do all that kind of manipulation with another language that are much, much faster. This concept of APIs and Python is being used in many, many different ways in different contexts. So, for example, we can have an API to connect to a data server and pull the data and look at it and push it back. We can connect to a machine learning framework that's written in a different language. It's a completely different code. Maybe it's online. We can use, when we communicate with CDAS, you had a lecture about CDAS a couple of weeks ago. We are using Python as the API to CDAS. So we don't have to understand how CDAS works that much, or the C code in CDAS to deal with it. We can do a lot of the work in Python. And also, if you're working with high performance computing, there are a lot of setups where you can do all the heavy lifting on the supercomputer, but you do the coding in Python. And this context, once again, this setup is done by other languages too, but this means that we have to think about how to kind of distribute or where we put the code and how to put the code in different, so that we're maximizing this kind of infrastructure. Coming back to the science stack, I just want to mention a couple of packages, a couple of use cases of Python that are really useful. I'm just going to go through them very quickly. But as I mentioned, NumPy is this kind of numerical base package that everything is based on. So you will, whatever you're doing in our world, you will use NumPy. SciPy is the one where you have statistical algorithms and you have ways of doing interpolations and a bunch of stuff like that, like higher order things. Matplotlib, sorry, not Platlab, Matplotlib is their big plotting package, which is horrible, but it's one of those plotting packages that takes a long time to learn, but once you've learned it, you can write code that does exactly what you do. You still won't like it, but it will do what you need to do. Matplotlib is actually what made me start to use Python 20 years ago instead of MATLAB, because I had to put in tons of work to get my figures right, but I could put in the work to make them right. In MATLAB, I often weren't able to solve the problems. Pandas is it's a way of manipulating tabulated data. So think Excel spreadsheet. So you have like a couple of columns and tons of rows. Or think of output from a glider that you have. So basically you have a couple of rows and then a couple of columns and tons of rows. Pandas is brilliant in doing that kind of work, like time series. It's developed primarily for economical time series and forecasting, but it's a very useful tool for that. X-ray is another basic method that we're using to get through and look at be able to work with gridded data. So output from satellites, satellite instruments, net CDF files that you would come from NASA or ESA. So X-ray is kind of the truck that we're using to work with that kind of data set. Scikit-learn is the big machine learning package that has been used by tons and tons of people. So this has become more or less a standard in the field of machine learning. So if you want to go in and start learning about AI and machine learning, Scikit-learn is a great place to be. Then Seaborn, stat models, and our improved statistics approaches. Pytrol, Cartopy are for doing maps, basically, and also a lot of processing of data, especially satellite data. So Pytrol is a package to do going from SWATs to grids and stuff like that. A bunch of kind of small scale work you need to do in the processing of satellite imagery is in Pytrol. SymPy, symbolic math, AstroPy, astronomy, and so on and so on. There are tons and tons of different packages that are well developed and well used, or very easy to use at the end. GeoPandas and Fiona are really useful if you guys are working with GIS, because that gives you a bridge between the normal file formats and data formats, data types that you use in GIS and Python. I use that quite a lot, actually. And going back to this question about data objects, as I was alluding to, there are, like, thinking about data objects and when you do data analysis is a very important and kind of a basic thing to consider, because the way we structure the data will be very important on how easy it is to analyze it afterwards. And as I said, if you work with tabulated data, so as I said, an Excel spreadsheet, a CSV file, output from an instrument, output from a meteorological station, whatever, Pandas is the best way to do that. Well, it's one of the really good ways to do that. They also can deal with time very, very well. So if you want to be able to do time ranges, or if you want to do, every month or every 3 months or something like that in your analysis, Pandas is where to go. When you look at climate data or any kind of gridded data, output from models, output from satellite data, output from sea surface temperature, ocean color, etc., and it's gridded in more than one dimension, then X-ray is kind of the arrow to take out and start shooting with. And then one thing that we don't normally use as much, but is very easy to come into, is databases as data objects, or output from databases as data objects. What you have here are, if you have data that you can slice and dice in many different directions, you maybe have data that are like you're interested in time series, but you're also interested in how it connects in space or different parameters. If it's very unstructured, then a database is normally the best way of storing the data. Also, if it's very diverse in structure or in coverage, etc. In Python, we use SQL Alchemy for that, for example. There are other methods to do that, but we also have these kind of packages that provide APIs to databases as well. And if you are now thinking, well, this is something I would like to do, how should I go on? You should look up something called PostGIS. That is by far the best database for what we are looking at. All right. Okay, so now we are in the point where we have decided that we want to do Raster.io is also great. Raster.io is an improvement or a higher level component of X-Array, which is providing tons of help functionality. There are other things like that. So yes, absolutely. Raster.io is kind of overlapping with the people at X-Array, doing X-Array as well. So This is not in any way a full description. And if anyone has any other suggestions of good packages and strategies, please let me know, and we can talk about those later. All right. So hopefully I've convinced you that you should learn to do some kind of language, learn a language, and preferably at least some kind of scripting language, and that you should start to be able to look at images yourself. Someone sends you an etcdf file or someone sends you a CSV file, you should be able to look at those files. And if anyone is sitting wondering what a CSV file is, it's basically just a comma-separated text file with numbers. An etcdf file is a self-documented binary file format for especially geospatial data. So what do we do next? Well, first of all, we need to figure out how to be able to work with Python. And there are basically 3 approaches that you can do. And I'm going through these not because I think this is super exciting, but because I've talked to so many people that have made more or less random decisions about this, and they could have done a better decision or a different decision if they had seen the picture. So I'm trying to kind of just create the map or show the map so you can yourself decide where you want to go afterwards. Anyway, so there are basically 3 approaches when you work with Python, and we're going to play around a little bit with all of them, and you might already do. But the easiest way to get into that is to actually do it in the web browser. You can like spin up and start playing with Python and these packages in a very, very short amount of time, and doing it without installing anything on your computer. All you need is to have a network access and a web browser. And the main resource, or the main thing that good question, I'll get back to that. So the main source for this is, the main ability to do this is Jupyter. So Jupyter is a collaboration between a number of groups that were doing different languages. So it literally stands for Julia, Python, R. So you can use it for MATLAB, you can use it for Jupyter, for Python, etc., etc., etc. And it is a web interface, or it's a way of programming these languages on the web in your web browser. I'm going to show how it looks in practice a bit later. But what has developed after that are people that are providing compute power, compute resources that you can access directly. One is called Binder. Google has something called Collaboratory. Kaggle has their own notebooks, and Microsoft Azure has notebooks. And there's something called Jupyter Hub, which is kind of a spin-off from Jupyter that also provide limited services. So in this case, if you start to Google any of these things and look at them, you can actually spin up and start playing around with data without doing anything, which is, well, I mean, without installing anything or doing anything with your computer. So this is the web browser. That's like the first level. Many people don't leave that first level. I have some colleagues that should leave that first level, and I'm discussing that with them. Where most people end up is what's called Integrated Development Environment, or IDEs. So what IDEs is a combination of a text editor and a way of running the code, but also to do things like debugging and being able to see where in the code you are, and so on and so on. This is a very, if you would go in and work in a company and you write tons of C# or Java or JavaScript, you would work within an IDE. So this is very much like hand-holding, trying to do things very, very well. Jupyter has a setup that is similar to an IDE, or basically an IDE, called Jupyter Lab. Microsoft's big IDE is called Visual Studio. And I think you can do Python development in that. But you also have Visual Studio Code, which is their open source, kind of use all the new cool languages, or like the terms that we are interested in now, and we want to be relevant thing. Visual Studio Code is very, very useful. I use that all the time. So if you want to do, especially if you want to do Python development and you want to do a lot of debugging and have a lot of help with debugging, Visual Studio Code is actually super useful. Spider is kind of old-fashioned a little bit. That is also an IDE that is fine, but I don't like it because it looks ugly. The other one, when it comes to like this kind of very inclusive, I'm coming back to Anaconda. The way that the way you would look into the other very inclusive kind of big company version is PyCharm, which is coming from JetBrains. It's not free; it costs a lot of money, but you can it really will hold your hand when you go through looking at data, because you can click on a variable in your text editor and you can see what the value of that variable is and stuff like that. So it's super useful especially when you're starting to kind of understand what's happening. Eclipse is written for Java, but it does have functionality for Python as well. And Funny is this very, very simplistic way of working on it. It's really cute, but if you want to really, really start and do something that no one else is doing, Funny is a great way to do it. Using an IDE also means that you need to be connected. You need to install everything on your computer, and you do most of the development on your computer, even if there are other options. What I normally do, or what a lot of people do, is that you have a laptop and you connect to a server or a workstation, or you're working with resources in your school or in your lab. And doing so, you normally want to work on command line. I'm not going to talk too much about command line right now, but that is something that basically is this text-based way of interacting with the supercomputer, with your own computer or another computer or a supercomputer. You can do this today. You can do this with Windows or Macs or Unix. It's coming from Unix or Linux, and basically you get this like little text editor, text window, and you write stuff in there, and it comes up. Many times that is a very good way to work. I did that for my first 10 years, where I had a text editor, and the ones that people normally talk about is things like Emacs or Vim or Nano. Or you can use a GUI text editor, or you can use Visual Studio Code, which can do these things as well. And then you edit a text file, and then you have a little window open so you can see your so you can run your code inside on your workstation or whatever. And then you see what's happening, and then you change your text editor, and then you go back and forth between your text editor and what's happening on your other computer. And that sounds horrible, but this is how people have been coding for 60 years, and it works, and sometimes it's actually quite efficient. As I said, Visual Studio Code helps to kind of bridge these different ways of working. You can actually open Jupyter notebooks in Visual Studio Code, and you can connect to a server with Visual Studio Code. Now it sounds like I am really promoting Visual Studio Code. I was always the gnarly kid in the corner that really disliked Microsoft. So it pains me to be so positive about a Microsoft product, but it is good. All right. So what do we do here? So how do we how do we continue with this? Well, what are you going to do next? What is the next step to do? And what are the different steps? Because now I've talked about this kind of general random stuff about languages and web browsers and Jupyter and so on. Well, if you know absolutely nothing about Python, but you want to start, the way I would do this, if I were you, if I were you, I would do something terrible, because I did terrible things when I started this. But what I should have done when I started doing this is that, first of all, learn to use the command line, because that will help you in many, many different ways. It depends on if you're on a Mac or a Linux machine, on a Raspberry, or whatever you're using. If you have a computer in front of you, you should know how to use that computer via the command line, because that will help you tremendously in the long run. Today, you can run Linux in Windows if you want to do that. That is actually a very good setup for a lot of the tools that we're using in Earth observation. The next step is to install Python. And the best way to do that is to use what's called Anaconda or Conda. When I said that there are multiple vendors but that you should have multiple vendors in a ecosystem. Anaconda or Conda is one of the biggest vendors for Python, and almost is a bit dangerously too important. Basically, what Conda is it's a package management system. What that means is that if you want to install Python, if you want to install a language, you can download some files from the internet and you can look at them and you can run some scripts and everything. And then at the end, you can do some kind of and at the end you just have like the language is there. And if you're lucky, there is some kind of interface that you can work with. If you would use Fortran, you would just be like, okay, now what do I do? What Conda is doing is packaging all these different pieces so they work together. Because think of it, if I was developing something and then someone else was developing something, we don't know if they work together very well. What Conda is trying to do is to make sure that we take the different versions and the different setups of different packages and streamline them so they work together. So I always suggest, and this is what we're doing at PML, always start with Conda and Anaconda. They are also a consultant group. So you can, if you have a very big job you need to do and you have money to do it, you can talk to them and you can hire them as programmers. That's how they make a lot of money. You can do like MATLAB and pay them a tons of money and they will help you install everything on your machines and get everything up and running. So they are a commercial entity, but everything they do, they also provide open source. And so Anaconda and Conda is kind of orthogonal from the way you're working with the code that should last. Miniconda is great. So Miniconda is so Conda installs tons of stuff at the beginning. So you have kind of an environment they think you need, but you might not even need that. So they have something called Miniconda, which has nothing but just this a package manager installed, and therefore it's much smaller. If you are worrying about space and you're worrying about that, you should look up something called Mamba instead, because we think that scientists are like cat, but computer people are even more like cat. Like this is cat herding we're talking about. So Conda became this huge, more kind of monolithical group that they did everything, and everyone's like, I don't like that. I want to do something different. And Conda tends to be slow sometimes. So then a group of people sat down and developed a almost perfect replica of Conda. So of Anaconda, that they called Mamba because we need to be funny. So we have Python, and then we have Anaconda, and now we have Mamba. So Mamba is basically Conda, but with much faster and much less resources being used. So if you want to start, you can definitely start with Mamba instead. But Conda is kind of like tons of information and user manuals, etc. So it's a great start. The two things to think about when you do these, when you start working with Conda, but any kind of Python, is you want to work in virtual environments. And this is something that has become extremely common everywhere in computer when people are doing computer development or computer processing, etc. And the idea is that we create this micro landscape or this micro system that is where everything works together and no one else can touch, so that we know it always works. You might have heard about Docker or virtual VMs. So that you can build up like this virtual little Linux machine on your Windows machine, or a Windows machine on your Linux machine. There are tons of ways you can do virtualization. It's really useful to look into it. But when you start working with Python, you almost have to start to do that. Because that means that you have, if you work on this project where you're looking at certain things and blah, 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 and everything worked well, you have the code up and running and everything is fine. And then 2 weeks later, you start to work on this GIS project instead. So you want to install another package, and that new package updates a couple of your the package you already installed. So it takes NumPy to a new version, etc., etc. And then 3 weeks later, you go back to the first stuff and everything is destroyed. Nothing works. This happens way too often for me. So the only solution to this in any kind of computer environment is to do virtualization virtual environments. Conda is doing this really, really well. There are other ways to do this, but do that. Conda and virtual environments. And the other thing you can do in Conda is that you can print out or have it write out a file. That's called environment.yml. This environment.yml file will tell you exactly how your setup looks like right now. That means that you can recreate it and actually get things to work. Sounds like, why am I talking about these really small petty things right now? Well, I'm trying to save you from yourself, because these things break. I break them all the time. I spend too much time fighting these. And TJ can probably give us so many war stories about this as well. The next thing you want to do is you want to think about how you will work. How are you going to work when you do this? Are you just going to play around without anything? Poetry is amazing. I didn't have time to go through that, but yes, absolutely, poetry is something you should look into. Think about how you will work. Are you gonna? Do you just want to play around and understand these things? Just use Google Colab and some Jupyter notebooks, so you just get a feeling for it. Or like if you go and do an ESA or NASA quick and dirty tour around what they can provide, do so. But if you're planning on doing more processing, then you want to think about, like, am I going to do it on my computer? I'm going to do it on another computer. How I'm going to do this? Someone else is going to use my code. So really think about how you're going to work and think ahead, because it's so easy to just start tinkering and trying to understand this. And the habits that you create really quickly kind of solidifies, and then it's very hard to kind of continue and change. It's hard to change at the end, or very quickly. So think about that, and then you decide your workflow. Do you want to learn an IDE? Do you want to learn Jupyter? Do you just want to use a text editor? It might be that you're investing tons of time for Visual Studio Code to know that extremely well, but now you can use that for your JavaScript project, or you can use it to write LaTeX. And just as a side note, Shuba's question there, you can actually do what you do in Overleaf using what's called in Jupyter, because you can write what's called Markdown, and there are functionality to do that. So you can't do it in Overleaf, but you can come from Jupyter books, and it's something called Quarto that can do exactly what you're thinking about that you want to do, which is combining code and text and create these kind of magic, kind of Harry Potter type documents where you can read the text and then you can run the code, and it's beautiful. But anyway, so decide your workflow, and then learn your tools as well as possible. Finally, another part where I'm trying to like how to learn not to shoot yourself in your foot too often is that one thing to always start to work with super early is version control and code repositories. Think about, so version control means that you have a piece of code, and then you can kind of put it somewhere else, and then you can keep working on it, and then you put the new version somewhere else, and you put the new version in the same place in the new version, and then you can go back and you can branch the data. So you start, this works, awesome. Let's see now, I want to try this other thing, and you can start to work on that, and then, oh, this works great. Now we can add that into the kind of main trunk. These kind of workflows are incredibly common among software engineering, and you should try to use that as much as possible. The most commonly used version control system that is used is called Git, and the most commonly used way of working with Git is called GitHub. So go and check out GitHub and Git and do that. This is not in the scope of this presentation, but do that. You will be so much happier when you realize that you did all this work and it totally failed, and now you can kind of backtrack and go in another direction. Anyway, All right, so for the stuff that I've been talking about, these are some links to those resources. It's like conda.io is to look at Anaconda. You can just Google Mamba and Conda and you'll find the Mamba version there. If you want to use Visual Studio, which I actually begrudgingly recommend strongly, you go to code.visualstudio.com and you can download the Visual Studio. And you can use Visual Studio for anything. It's a very, very broad, the use cases are extremely broad. There are a couple of ways of learning Python. My preferred method, one that I use myself and I always tell people to use, is there's a guy called Zed who has developed a number of curricula that he called Learn XXX the Hard Way. And he has a package called Learn Python the Hard Way. And what he wants you to do here is basically do the opposite from in his curriculum is basically the opposite from what I've been talking about, which is he wants you to start with simple methods. He wants you to write everything, not copy and paste. And he kind of just pounds in basic understanding of computer science, of algorithm development, and the language. If you go through that, it's like 10 or 15 units. It's not free. It's like, I think $20 or $29. But if you get his books and his web his videos, that is a very good way to learn Python. Another one thing I've been looking at that seems really, really nice is learnpython.dev. She set it up with Visual Studio as the main source. So she will go through how to set up Visual Studio for Python, etc., etc. So that's a really great way to do it. There are tons of other resources, like just Google Learn Python. Or if you have a specific need case, you can always email me and I can kind of guide you in the right direction. When it comes to Git, Git is hard to learn. It's annoying. You should learn it. It will help you. It's great to have on your CV if you're younger. The basically best way to start is to go to their kind of official book, which is gits-sem.com/book/n/v2. There are graphical user interface. There are apps that can do Git for you, but they only help you to a certain extent. This is something you should just, yeah, it's broccoli. It sucks, but you kind of need to learn it. Great. So I'm just going to talk very, very briefly, a couple of minutes about just like how Python is structured. And then I'm going to show you a super simple example just to give you an idea how Jupyter Lab works or looks like. And that's basically my time. So I'm sorry that I can't provide a better Python class or teach Python, but in an hour, this is what you get. All right, so when we write code in Python, and I'm going through these once again, it's like avoiding people to shoot you in your foot. Like you might remember this when you start working on it. When you write code in anything, you want to kind of separate the code in different ways. And the way you do that in Python, and the terms that they're using are, so you have the code, which is just like a list of commands. You can kind of separate them into functions. Functions means that you have an input and an output. And then those can be added up into classes. And then those classes can be added up into text files that are called modules. And those modules can then become packages. And a package is everything I've been talking about, like NumPy, etc., etc., etc. They are considered packages. So that's a kind of a self-contained little group or piece of functionality that you can use. And I'm just going to show you this super quickly. So what I'm showing you here is, first of all, Jupyter Lab. So this is Jupyter Lab. This is an IDE. It looks very similar to Jupyter. On the left side here, you see just a list of different files. On the right side, on the top here, you just see a couple of notebooks that I have opened. So notebooks is kind of the basic source of where you can work. In Jupyter Lab, we can also open, oh, sorry, I went to the wrong one. We can also open code. So this is a pure text editor. And this, what I'm using right now, this would look the exact same in Safari, but you can actually have a freestanding application, which this is. So this is just, I used this in a terrible way for a colleague where I asked him for the worst piece of code he'd ever written. And he gave me this one, and then I used it as a lecture to show how to take this kind of MATLAB code and create a Python package of it. So what this code does is that it just writes down, it reads values from a Argo float and it plots it. That's all it does. But you can see it's like 369 lines, and I have no idea what any of this does. I had to go in and read it everywhere. And you can see, talking about version control, you have all these teal things that is commented areas. These are things that we're not using. So basically, if we need to have two different functionalities, we just like comment out the functionality we don't need, and then we add it somewhere else. So it's like, it's horrendous to work with and so on. And this is not my anonymous colleague's fault, because this is a great code. This is how we all program. But I just wanted to show it a way of like how you can do this better. And just going to show you how it looks like when you do it the right way. So here I've taken this huge long piece of code and kind of set it up as you would do in Python. And on the left side here, you see I'm standing in a folder that's called new bioargo. And in the new bioargo, I have a number of files. So these are, as I showed before, modules. The first module is called init. That is just like the initial, that's the package part. In this case, what I've done is that I have a class. I'm not going to go through classes, but what I get here now is that when I look at file IO, for example, I have a function that I call read variable that just does that. It reads the variable. The text I have here is commenting that I can use from the command line. I can see this all the time, which is great. And then you can see that there's a very small pieces of code here. And then we have the plotting function, which is suddenly very small, like different types of plotting functions. And then finally, we took all those weird commented out stuff and put it in one file. So now we have these 3 different files that do the exact same thing in a couple of lines that this earlier code I showed did. So it's a way of getting things much, much cleaner and much, much more easy to understand. So when you start programming, this concept of you have your code, you have your functions, you have your methods, modules, and your packages. Do use that. Don't skip that part because it's super, super useful. And then finally, what I'm going to do now, because of time, is I'm going to show you a couple of examples. First of all, I just want to run this example I showed you before. So this is this example of the loops I showed you in the main presentation. And this is how Jupyter works. So basically you have this cell up here. So every time you start writing in Jupyter, you create what's called a cell. And when I click Shift and Return, I run that cell. And as I told you before, we need to tell Python what we want to use. So we need to start telling them that we need to use the science stack, and we import NumPy as NP. Now we have access to the science stack, and we call it NP. We create those, as I said, those arrays. So array A and array B, and we call them ones. And then we create array C, which is with the zeros. And then we run them, katunk. So you can see now it says 22, 23, 24, 25. That is just like the order that these cells have been run. We can look at them. So you see there says nothing here because this cell hasn't been run yet. But if I click on it, I can see the content of array C. And then we can do array D, katunk, and we can look at it. Great. So this works. But what I want, the reason I showed you this, before was that we wanted to see how fast it is. So what we can do now is we can take this and we can create a function instead. And as I said before, functions are used to as a way of kind of separating things from each other. So now I create a function that I call add, and I will submit into the function these two arrays, array A and array B, and then I want to push out and we need to do the same kind of indentation for functions. Then I want to return array C, and then we want to add array C to that, just for fun and entertainment, like that. All right. So now so now we've created a function that we call add, and we can just do like this, add or A, comma, or B. And we can run it, and we get what comes out of this function now is array C. The reason I did this is that now we can rewrite this. And there are in Jupyter, there is called magic functions, magic functionality, which is, if it starts with a % sign, that means that it's kind of not Python, it's kind of Jupyter's own stuff. What timeit does is it will run this, actually, let's not look at that, let's look at this one first. Let me start with time, and I'll show you why. Okay, we run time, but this tells me is like how fast did it take to run this loop, or to do this, and it will tell me that it took about 6 milliseconds. We now do instead time, and we do the other one that I said was a much better way. That we see we get 547 nanoseconds. So it's basically 10 times faster. But then if we do this again, because in Jupyter, we can kind of like just click and shift return on any of these cells and it will be rerun again. You see it varies a lot. And that's kind of annoying if we wanted to like time this thing. So we just do timeit instead. What it does now is that it runs a number of loops and it takes the average value. So in this case, it's 5.84 microseconds after 100,000 loops. And you see that the one I did before, the timeit one, was 5.8 milliseconds after 100 loops. So this is, in this case, about 1,000 times faster. And the difference between this and the one time we only run it once is that it takes time to kind of start up the process and figure out what we're doing, and it takes time to write out things. But that is not part of the difference between doing a loop and doing this kind of go down and see with a big data type and then combine the other data type and then bring it back to Python approach. All right, I'm going over time a little bit, but I'm just going to show you a tiny bit more. And you can just scream at me when you get bored. What I'm going to show you now is about how to use Xarray, and hopefully this will work. So this is once again a Jupyter notebook, and what I do here is that I import, as I say, Xarray, I import NumPy, and I import a plotting library, this matplotlib plotting library. And what the final code does here is just telling the system that I want to show this online, or within the package, within the notebook, sorry. All right, so now those are all imported. And then I create a connection to a data set. And in this case, I'm just using a very small data set, or not small data, but I'm using a test data set of sea surface temperature. So this is NOAA data. But what this means, what I do here is that I connect to this online resource. You see it's an HTTP address, and I can create what's called a handle or a instance. So this DS now is basically an object. It's a little piece of it's a little object that contains information about everything in this big data set. And if I just click on it, if I just do like this, I can see what's inside. So I can see which dimensions there are. So it's latitude, longitude, time. And if we click, well, that's all the information there. I can see the coordinates once again. So the dimension and the coordinates in this case is the same. They don't have to be. We have the data variables. and the SST is the most common one. And here we can see the dimensions. So you see the time, latitude, and longitude. The nice thing with, as you can see, this is a net CDF file, as you can see up here, NC. The nice thing with net CDF is that, first of all, it does understand that it is a gridded data set, but it also, you can also provide a bunch of information. So in this case, you can see this is the NOAA Extended Reconstructed SST version 3.0, was created in 2007, and it goes for a amount of time, etc., etc. So this is all the information you need. If I write, this is very common to do in NumPy and Python and so on. It's like, so basically we use this dot to show we have this object. Now we look at in a subpart, a little bit part of this object. And in this case, I want to look at this variable called SST. So I just write that. And now I can plot out, I can see the more information about that. I can see more attributes. So this is a way of digging down into this data structure. And once again, this is all done against the server somewhere else. So at this point, the only data that I have downloaded is the data, these metadata. So let's do a plot. I can, in this case, what I do here is that I use this matplotlib package, and I tell it to use the longitude that is coming from here, because I do ds.long, ds.lat, and then I want to do the last, I will plot the last image, the last day, because if you look here, you have the dimensions is time, latitude, longitude. So we say that we want to be time to be -1, which in Python language says the last one. Then we want to have all the latitudes and all the longitudes. We get this nice figure. So that's very easy. To look at the time, because why not? So this is how, so you can see that we can access these other subparts of the data type very easily. And we can plot the time. What I plot here is one grid cell in this data set. And what you can see here, first of all, the way they did the sea surface temperature from 1860 to 1910 looks very different from what happened afterwards. So you can see that there's a change in methodology here. But so that's why it's always good. And this is what I'm saying, like, just having the ability to do these things are super useful. Like you want to be able to look at the data and plot it. Xarray has a bunch of cool functionality. One of them is that you can do kind of statistics and means and aggregates on all the data, on these kind of data arrays and these data objects very quickly. So what I did here was that I created a mean of a sea surface temperature over axis 1, which is in this case latitude, because everything starts with 0 in Python land for reasons. And then when we've done that, now we have a new object that has time and longitude. So now we do a new mean, an extra mean on that thing that was created, where we also do axis 1. So now we remove longitude. So that means that we only have left time and sea surface, so this, it means sea surface temperature. We've removed latitude and longitude, so we can plot the average sea surface temperature versus time, and we see this. Okay, this looks interesting. We see that the area where we had weird values have a very different structure than the values where we kind of everything looked similar. Now I just import a linregress package, because we can do anything in Python. It's always called batteries included because there's so many functions included. With that, I can do a linregress. So I can do a linear regression on, and in this case, I'm not taking time. I'm just doing a values from 0 to the length of this data, the mean sea surface temperature data set. And from that, I get a slope, and I get an intercept. I get an R value of 0.5, and I get a p-value of minus up to the, well, very, very small p-value. So we definitely have a trend. It's not super high, but that is because we're kind of trying to trend it like this. So let's remove this nonsense over here. And the way we do that is just using a data write function where we set, we want time to always be larger than 1910. And then we create a new little data object, now new little bag of data. So instead of DS, we have now DS2, which is different because we truncated the early times. And we created, oops, and we did wrong. We created a new mean SST, and we plotted. And now we can see that it starts later, so that looks much more reasonable. And you can see this strong linear trend in the data. And it's kind of hardcore. And we can do linear regress, and we can see that now the slope is twice as high, and the p-value is even more ridiculously lower. And I would say that the global ocean is warming from this. All right, this is just a way of showing how you can work with Jupyter Lab and with Jupyter Notebooks, and how to do a very, very simple analysis of a data set that where we just started with a link to just a web link. So this is where I'm going to end, because I hope I can have given you a little bit of an idea of what you can do and how to proceed. This is not, there are no perfect instructions, because there's so many ways to do this, and all of you have an individual way of doing it. So you all want to think about how to do it. If you have any questions, especially you guys that are coming here, please just let me know, or talk to us, and we can definitely help you more. Thank you so much for listening.
Thank you, Bror. That was really, really good presentation. I learned lots of things again. So that's good, and also nice that you give a little demonstration in Jupyter Lab. Also, I don't know if you see the chat, but things came in, and people are saying thank you. So there, you've already answered some of the questions, because you were very skilled in giving your lecture and looking at the chat at the same time. But I'm going to go through some of the questions that you have not answered yet, and maybe touch upon some of the things you've already answered, and maybe you can give some more clarification on that. So I am going to start with sort of general questions from Python and then go from there. There was a question about how Python manages memory. And this is maybe related to a broader question about what computer system do you need to actually work with Python?
So it's a very good question. The way Python handles memory is garbage collection. If you talk to people that are doing Python development or Python developers, they will say that Python is amazingly good at doing garbage collection and handle memory. I often run into like the little dirtiest corner where it doesn't work is where I end up for some ungodly reason. There are ways of getting around that, but basically if you're working in Linux, and today I would say on Macs, it is very, very memory efficient. It's more of an issue about so when we work with these data structures, you see that it says, for example, float 32 here. That means that you use 4 bytes, so 4 set pieces of 8 to define a number. That's a lot of that's a pretty high precision. The default is float 64, which is twice as big. So just like looking at how precise do we need to describe the data is helping a lot when it comes to memory. In general, if you work in one processor in one thread, like if you do one thing at a time, it will do well all the time. The time when Python gets really, really sad is when you do stuff in parallel. And there are solutions to that. So if you get stuck on that, let us know. And there are solutions to that too, but it is in parallel mode that memory becomes a challenge most of the time. But GC is the answer to your direct answer to your question.
Thank you, Bror. There was a question from someone who's at the moment a MATLAB user and has not used Python before. Actually, they have 2 questions. The first question is, are the packages that Python requires equivalent to MATLAB's add-on toolboxes, or are they fundamentally different? And our second question is, do Python users create functions that can be shared among the community? A similar system exists for MATLAB's file exchange.
Yes. So the first question is ish. It is the same thing, but it's not developed. There's no MathWorks. So it's developed by different groups and so on. The closest to MathWorks would be something like Continuum or Anaconda, the big organizations. But the functionality is very, very similar. But because they're developed by volunteers, often there might be differences in quality and skill. On the other hand, I worked with a lot of add-ons for MATLAB, and sometimes it's the same thing for MATLAB as well. All modern languages have ways of distributing code to others. The other main reason why I left from MATLAB was because file exchange was terrible. The way it works in Python is that, I should say like this, the way it works for us in Python is that you can either do it via something called the Cheese Shop or PyPy. Someone had commented about Poetry. Poetry is a package to take what you've developed, package it up so other people can use it and send it in a very structured and organized way, so everything is right, and also take care of all the dependencies, like I need NumPy, I need matplotlib, I need this and that, and kind of create this little bag of stuff, and then send up all that information to a server somewhere that's called PyPy, so PYPI, or the Cheese Shop, because everyone thinks the Monty Python is very funny. And from there, you can just use a command to download, to install it. So if I need one of my packages, I can write pip install proimap, and I don't need to know where it's stored or who has done it or whatever it is. There is a level of unsecurity in there. So what Conda does is that they have this kind of formal single stream way of installing stuff, and then you can create your own little package system on the side, and then you can kind of balance those things. So to be like a first-class citizen in Conda world, you need to be vetted and befriended by the Conda people. But if you want to do something on the side, you can do that as well. So as with everything with Python, it's like there are too many answers, but yes, you can absolutely do that, and you can and normally these things work together.
Thank you, Bror. There's a question about learning Python, and it's, well, I guess it's not a strange question, but it's the way we learn a new language or Python. And someone was asking, how do you see ChatGPT or other AI tools help us to learn new languages, and how can we anticipate new developments to improve our code?
So it's actually a pretty good question. When it comes to learning the language, I would stay away from it as much as possible, because, and this is what this learning the hard way methodology or philosophy is doing too. Basically, you want to start with figuring these things out by yourself, by doing mistakes. Normally, the best way to learn is to have a small project. Okay, I'm going to do the figures for my next paper, or I'm going to figure out why my electricity bill last month was so high, and I'm going to do this in Python, and it's going to be painful, but you start with, you have a need, you have a question, you want to do this, and then you start to learn the tools to get to that point, and nothing will help you with that. It's kind of learning a language that we talk, in the sense that you need to have the basics. Once we have them, once you start to see the structures and like you understand, you can read the code, you can understand that, then ChatGPT can be tremendously helpful by telling you how to do certain things. The problem with that is that it can help you to tell you stuff, but when we program, I shouldn't say all of us, but many of us, when we program, we don't do very repetitive code, because that is also something that Python is trying very hard to remove. So if you're working with an iPhone app, or if you're doing web app in React or C# or something like that, you might have to develop tons of views and images that look kind of similar. ChatGPT can help you with kind of redoing that work constantly, because it's like tons of code, but it's not very complicated. But for us, it's more that you might have 10 lines of code, but you have spent a day to figure out what those 10 lines of code are, because it's a very specific problem space that you're working within and so on. So I don't think that ChatGPT will help us tremendously, but I think that it's very useful in where you're more operational, when you're doing more of this kind of boilerplate type of development. TJ has a comment there.
So I've been playing around. I mean, I think many of us in the community who are coding have been playing around with ChatGPT and GPT Engineer and things like that. And it's very powerful for bulk building, as Paul said, standardized things, boilerplate code. It's because it's a language model. It's designed to predict the most likely. I mean, it's a very advanced predictive text, basically. So where it starts to fall down, and I think this is basically what Paul was saying, is where we want to do something really novel, truly new, edge case, hasn't been done before. That's unlikely to be a prediction of the code. And I've definitely had cases where I've been trying to, I've thought, okay, I'll see if ChatGPT has a solution to my problem. And, you know, when you give it its own error messages back, effectively it ends up stuck in a loop, flopping between two different wrong answers. And you say, this is wrong. And it says, okay, try this. And you say, that's wrong. And it says, okay, try option B. And you just get stuck. And it's because, you know, the problem that you've encountered, there isn't enough training data on it, or, you know, some packages have been updated since it was last trained. There's all sorts of reasons that it can be an issue. So I think it's useful when you're coming to something fresh and you think, you know, I don't know how to plot something with bigger fonts than I have now. That's a standard problem. It's been done so many times, easy. But if you're saying I want to do something truly novel and new with the data, then that's something you have to sit and think about for a bit longer and kind of deal with yourself. But yeah, for like asking how to make plots pretty or change an axis label or something like that, ChatGPT will have quick answers. It's effectively a faster way of going through places like Stack Overflow or other code discussion forums.
And also remember that because you get an answer, it's not the right answer. My wife is right now writing this nightmarish report now, just like a 100-page report for the state of New York about postpartum depression, and she was like, okay, can I have the ChatGPT write this section? And she was like, write the section about blah blah blah, and this is this, and we include all the legal like all the old laws about this, and it created this perfect thing. And she was so happy. I was like, this is amazing, because she was like, she was texting me during time. It's like, it does it. It's like, it's 4 lines ago. This is perfect. This is exactly what I want. This is so great. And then she was like, and then it's like, oh, can you just add references? And it added all the references and so on. And then she just wanted to go and like pick up the references and put it in the reference list, and realized that it made up all the references. It made up the legal basis for this stuff. Like everything was just this science fiction thing. Like there is a world where this could have happened. It wasn't our world, but it could have happened. So it's like,
yeah, here I have seen ChatGPT invent properties of packages. You know, it'll say, oh, use this dot mean, and then obviously that property doesn't exist within the module, but it predicts it will, or it thinks it should.
Yeah.
So yeah, you definitely. I think the most important point is being able to understand and interpret error messages, and you can't do that without learning some Python code to start with. So get your foundations, and once you've got that and you can understand and interpret an error message, then you can interact with ChatGPT much more quickly, because the code will be wrong. It will have errors in it, and you need to understand what those are.
Yeah, so instead, go to your bank website, download your last couple of. Normally, you can download your statements as a CSV file. Download that, learn how to read that into Python, and then figure out where most of your money went for the last 3 months. That's a good way to learn Python.
That's a good challenge, Bror. I might try that myself, although I know how to code in Python. But it's a good example to get started with some actual data and something fun maybe to start with. Thank you both for your answers on that question. There are a couple of questions related to the tools of programming that you mentioned. So those were your integrated development environment, your command line, and what else did you mention? One other thing, web services.
Yeah.
So there was one question that asked, what is the difference between an integrated development environment and a command line? So they specifically mentioned Visual Studio Code and PyCharm. Are these not the same thing?
They can be. So Visual Studio Code, so the difference with it is that, and this might be a bit opinionated, but I don't know. Basically, the difference is that one way of working is that you have a dedicated text editor that you do all the work, and then you have that text editor edited on your file system, and then you run it via command line. So you have these two things completely separated, which means that your text editor doesn't know what's happening on your command line or in your Python REPL, what is called or whatever. Or if you're compiling, it doesn't know what your compiler is doing. If you have an IDE, those things are integrated. That means that when you write the text in Visual Studio Code, you can click on a link and it will run the code for you, and it will see if there are any errors, and it will tell you what those errors are. So it kind of integrates all these functionalities of debugging, of linting, which means like it's making sure it looks pretty according to standards of this language. It makes sure it can run it to make sure that that is correct. It will tell you if you haven't imported the right module, for example, you will get a little wiggly line under it. So it's much more intelligent. Visual Studio Code starts as a text editor, and then you can throw more and more and more stuff on it until it becomes a full-blown IDE. PyCharm starts as an IDE, and then you can kind of squeeze it down to maybe become a not as good text editor. So if you think of it in that sense, like Visual Studio Code started as just a text editor, and then PyCharm is on the other side. PyCharm is great, but it's a 800-pound gorilla. There's a lot of stuff to learn.
Thank you, Bror. There was another question related to the integrated development environment, and which one would be the best for debugging in Python?
Yeah, so Visual Studio Code is actually surprisingly good. PyCharm is developed to do that, so I think they would be best in class. JetBrains are doing a tremendous amount of good job there, and there are people that I have kind of heard about people that basically cannot program without PyCharm and other JetBrains systems. So I would say those two. The difference, once again, is that PyCharm is a paid product. I don't know if it even has a subscription. But then they will have videos to tell you how to do it. There will be classes in how to do it. It's a very kind of well described. A lot of the stuff in Visual Studio Code is done by volunteers, and one guy had thought about it. So you don't. What you pay for in PyCharm is that someone has really sat down and thought about how this should work. And in Visual Studio Code, it's much more ad hoc. Spider, as someone just asked, it's an older, smaller system. So they are still an IDE, but there are tons of stuff like IntelliJ, or like you can have, there are tons of things in Spider that the Spider doesn't have. So I'm not working too much in Spider. If you like it, absolutely use it. The reason I do it is I find it visually kind of unappealing, which is a bad thing. But at the same time, Spider, I think if you install Conda, Spider will be installed default. So if you're working just by yourself with Spider, Spider is great. But it's like the little monkey running around beside the 800-pound gorilla.
Thank you, Bror. You talked about a couple of Jupyter tools, and there was a question about the difference between Jupyter and Jupyter Hub.
So Jupyter is kind of the bigger, that's like the overarching term. Jupyter Notebook is is a new Jupyter Notebook. So you can install Jupyter and then you can have it spin up a Jupyter Notebook like this by itself. That is totally fine. If you want to have this integrated environment, which this whole thing is with I mean, I can, as I said, I can open a text file, I can open images, etc., etc. Then that is Jupyter Lab. Jupyter Hub is a server that you can use to run, no, I should say it like this. So Jupyter can always be is a double setup. So you have a server that runs Python somewhere, normally locally, but it can be somewhere else. And then you have this web browser web page, or in this case, this individual app that is talking to the server. So the way you start Jupyter Notebook on your local machine is that you write Jupyter -- notebook, and then something happens, and then pop up, suddenly your Safari window pops up and you can see it there, because those two are completely different. Jupyter Hub takes that server component and make it multi-user. So if you want to run a system for tons of students, or for like you have a supercomputer, you want people to have access to that, and you want to be able to have people to log in and log out and all those kind of extra admin stuff, that is what Jupyter Hub does for you. So it takes this server that is in principle built for one person and make it multi-user.
Thank you, Bror. There was another question related to Jupyter Lab and whether you could use this on a Windows machine.
100%, yes, you can.
Okay,
you can either do it through as a web app in a web browser, but I'm 99% sure that this single or like individual app is also there. It's basically an Electron app.
Yeah, perfect. Thank you. Those were the sort of outstanding questions. There were a couple of questions about Anaconda and Miniconda and the different options there, but you've already answered all of those. There was a question related to whether Jupyter can be linked to Overleaf, but you've already answered that question as well. And then there are some webinar logistical stuff questions for us, which you do not have to answer. So thank you very much for answering those questions and for your lecture today. I've seen many positive comments, so scroll down the chat for a little bit of good vibes there.